When the circumstances are right, regression discontinuity can be an excellent way to extract causal estimates from observational data. In this video, I'll give you a prototypical situation where RD is applicable and explain how it works. I'll also describe situations where the method fails and say a few words about fuzzy discontinuities. Suppose we want to know if giving high school students money to go to college improves their grades once they get there. This is usually a tough question because students who win scholarships are different in many ways from students who don't, and it's hard to know if differences in grades are due to those things or to money from the scholarship. The National Merit Scholarship is awarded based on scoring above a certain threshold on the PSAT, a test usually taken by high school students during their junior year. The key to estimating the effect of the scholarship is that threshold. Students who score just below or just above the threshold will be similar in characteristics such as IQ or study habits, but the students above get the scholarship and the students below don't. In essence, RD compares the students just below and just above the threshold and considers the difference in outcomes to be the program effect. Let's look at some pictures. Imagine that the x-axis is the score on the PSAT, and the threshold for getting the scholarship is right here at about 0.5. The y-axis is GPA, where GPA has a maximum value of 1.5. We expect grades to increase with test scores normally, but we also expect a discrete jump due to the scholarship at the threshold. The size of this jump is the RD estimate of the effect of the scholarship. In this picture, the relationship between the x, the test score, and the outcome is approximately linear. This is the best case scenario as we can use data from the whole distribution to identify the slope of the line on either side. Even when the underlying relationship isn't linear, however, we can still do an RD if we expect a sharp discontinuity at that threshold. That's what's going on in this picture. As long as the relationship between x and y is continuous outside the discontinuity, the method should work. Problems can arise when the underlying relationship between x and y is continuous, but has a kink near the threshold. That's what's going on here, and it's easy to accidentally interpret this as a discontinuous jump if we fit a linear function on either side and look for a difference right here. It's straightforward to estimate the RD with a regression. If you're willing to assume the underlying relationship between x and y is approximately linear, you just need to estimate a pure linear regression model, where the outcome is linear in the x, and you add a dummy variable for whether or not x is above that threshold. In this case, b2, the coefficient on that dummy variable, is our estimate of the program effect. You can also fit a polynomial through the data and include the same dummy variable. Again, the coefficient on that dummy will be the RD estimate of the treatment effect. If you want to allow for a different linear trend on either side of the discontinuity, you can estimate this slightly more complicated model. Define x prime to be the distance to the cutoff, and the fitted line will have a different slope on either side, with beta 3 being again the estimate of the RD effect, the coefficient on the dummy variable. We use distance to cutoff instead of the actual value of x in the model so that if there's no effect, the two lines connect to each other. One thing you might worry about is that there's something else driving the discontinuity that you observe at the threshold. Perhaps another related program uses the same cutoff. In that case, you can look for effects in outcomes or covariates that should not be affected by the treatment you're evaluating. If you find any, they would be evidence that something is going wrong. Similarly, you might wonder if you're picking up a non-existent discontinuity just because your outcome function is jumpy. You can test for this by looking for significant effects at other values of the independent variable that should not be thresholds for the program you're evaluating. And third, if individuals can manipulate x to push themselves over the threshold, the RD estimate's invalid. One way this could happen, in our example, would be if unscrupulous kids were able to ex post change their grades to push them above the scholarship cutoff. In that case, we wouldn't know if the observed differences in college grades were due to scholarships or other differences between students who cheated and those who didn't. Sometimes a threshold is not hard and fast, but just makes the treatment more likely. This is called a fuzzy discontinuity, and it can happen when there's a publicly suggested cutoff that's not enforced. In this case, you can just use two-stage least squares and consider being above the threshold as an instrumental variable and control for the underlying variable continuously. At the end of the day, regression discontinuity is an excellent way to estimate causal effects when you don't have explicit random assignment, but you do have a variable that determines the treatment such that when an individual is above the threshold, they get the treatment, and when they're below it, they don't. If you want to learn more about RD methods, I highly recommend Chapter 6 of Angrist and Pischke's excellent Mostly Harmless Econometrics and Lee and Lemieux's review article on RD in the Journal of Economic Literature.